So we want to talk about how friction happens or how motion happens. And we're going to do that by looking at kind of the classic horse and cart problem. So here's Newton's dilemma. It's not a dilemma Newton had. It's a dilemma that students have when they misapply their understanding of Newton's second law and Newton's third law. And so this video is for you to help you figure out how to apply second law and third law correctly. So the dilemma goes something like this. A cart is attached to a horse, and the horse pulls forward with a certain amount of force. According to Newton's third law, the cart pulls back with the same amount of force. And so I've done a schema. This is not a complete schema, but we've got the cart and the horse are interacting, and there's a force on the cart by the horse and the force on the horse by the cart. Because this is the same interaction, we have a Newton's third law pair. And so the force on the cart by the horse is equal to, but opposite direction, as the force on the horse by the cart. Okay, so this is my Newton's third law pair. It's this step. Okay, so if the cart and the horse pull against each other with equal amounts of force, then the forces are balanced and the cart cannot accelerate forwards. Thus, motion never occurs. All right, so hopefully you guessed there is a major logic error here. Okay, major logic error. And so we're going to try to figure this out. We're going to look at one statement at a time. So a cart is attached to a horse. That's the problem, okay? That's where the problem starts. And so that has to be true, because without the cart being attached to the horse, then we've got nothing. Okay, second statement. The horse pulls forward with a certain amount of force. That's how the cart gets in motion. So again, this statement must be true. Third one, according to Newton's third law, the cart pulls back with the same amount of force. So the idea is I've got a single interaction between the cart and the horse, and so I have a Newton's third law pair. So these are the same length because FHC and FCH are a Newton's third law pair. Okay, so we're going to accept that as true. So if the cart and the horse pull against each other with equal amounts of force, all right, so this is Newton's third law. Newton's third law, so it must be true. Then the forces are balanced and the cart cannot accelerate forwards. So this is where we have our logic error. There's something wrong with that statement. There's something wrong with the statement. And the problem with this statement is that the free body diagram is wrong. This is not the free body diagram of the cart or the horse. All this is an illustration of Newton's third law, of the Newton's third law pair between the cart and the horse. So a correct free body diagram, so a free body diagram visualizes all of the forces acting on a single object. Okay, all of the forces acting on a single object. So for example, if we wanted to look at the cart, okay, we know that obviously there is the force on the cart by the horse. We also have the force of gravity on the cart by the earth. We know that we have a normal force on the cart. I'm going to call it by the road. And then we might have some friction backwards. And so we're going to have the force of friction on the cart by the road. These two are equal because the cart is not moving in the vertical direction. We know that these two, their length depends on whether the cart is accelerating or not. If the cart is accelerating, then these are different lengths. So for example, if we're just starting out in motion, this is going to be very small compared to this. If they're moving at constant velocity, these two are going to be the same. But notice what does not appear on this diagram, okay? Notice what does not appear on this diagram. This force right here is not on the free body diagram for the cart because it doesn't act on the cart. It acts on the horse. I can tell it acts on the horse because that's the first letter. Okay. Not on the free body diagram for the cart because it is not a force acting on the cart. Okay? So, motion of an object is based on the forces acting on that object only and not the forces it is exerting on other objects. So this is the problem with the cart and the horse problem, is that people think, oh, well, Newton's third law, these are balanced, so it can't move. But the problem is these forces are acting on different objects. This force, I'm going to change colors. Whoa, I did not want to do that. Stop. Okay. Okay, this force acts on cart, and so it will be on the free body diagram for the cart. This force acts on horse, and so it will be on the free body diagram for the horse. So these two forces act on different objects. Okay, now we're going to go on to another topic. We know that we've got friction, and we want to really know which way does friction point. So we know there has to be friction between the ground and the horse in order for the horse to move. If the horse were on ice, it would not be able to move. So we know friction is what's causing the horse to move, and we need to figure out which way the force of friction points. And so we're going to do a bridging example. So I want you to get up, and I want you to stand on both of your feet. And then you're going to lift up your right leg and start to move it forward to take a step, okay? So you're going to step forward with your right leg in the process of walking. Which direction do you push your left leg, the one that is still on the ground? Push it forwards or backwards? And the idea is that in order to walk, you actually have to push your foot backwards. So let's see what's happening. So here's the surface, and if this way is forward, and here's my foot, and here's my right leg. Okay, I'm just going to ignore this leg. I'm too challenged as it is. So if I want to go forward, I actually have to push back, like on my toes, which means if I think about the surfaces sliding, so if the object, so that's foot and road, started sliding, the foot would slide backwards. So the direction of friction on the foot is forward. So if these were going to slide, the foot would slide back, and so the force of friction would oppose the motion, and so friction would be that way. Okay. So if you think your leg moved forward, both of your legs go in front of your body. Remember, your right leg moved forward to take a step. In order to walk, you have to push your left leg behind and you move your body forwards. So you push backward off of your left foot in order to move the whole body forwards. And so again, if there's a slide, the slide would be your foot sliding backwards, and so friction has to point forwards. All right, so there must be friction between the ground and the horse in order for the horse to move. If the horse were on ice, would not be able to move. Which way does the force of friction between the ground and the horse point? Okay, it has to move forward. If the horse is moving forward, there must be, and I'm going to say external force pushing it forward. So something not on the horse. And that external force is friction. So in other words, i.e. friction. So the forward motion comes from friction pushing the horse forward. Okay. A block is sliding to the left and slowing down because of friction. Which direction does the friction force point? Okay, so if the block is sliding to the left, friction opposes the direction of the slide, and so therefore it's going to, friction force points to the right. It's always parallel to kind of the sliding surfaces, and so friction is forwards. Okay, there must be friction between the ground and the horse in order for the horse to move. Which way does the friction point? The hooves are moving backwards, or pushing backwards. Which direction would friction point? So, it points forwards. Okay, so the horse and the cart are moving forward. The hoof is pushing backwards, which would cause a slide backwards, and so the direction of friction is forward. Okay, so the horse and cart problem is actually a tug-of-war problem. Any tug-of-war has this same form. And so I'm just going to do a quick schema. Just make sure you are on the right track. So we've got cart and horse. And we've already said there's a force between them. You might wonder what kind of force. I would call it a tension force. So we also know that we have the earth. And I'm going to make that in the same bubble as the road. Okay. All right, we know that we have the force of gravity, which I'm going to call weight. We also know that we have to have friction. The horse definitely has friction. If you want to leave it off the cart, you can, but it should be there as well. And then we can never have friction without a normal force. I'm going to change colors just to distinguish. So between the horse and the road, we have normal force. And between the cart and the road, we have normal force. Okay, so that should help you. Just one more thing that I'll do. If we do our boundaries, we can see that the horse has 4 interactions. So that means I'm going to have 4 forces on the free body diagram. And same thing with the cart. I have 4 forces, 4 interactions, so 4 forces on free body diagram. Okay, you are going to start a notability file. You're going to work out some problems. And the first thing is that you need to write down this information. So you should stop the video and open notability file and write down this information. The cart has a mass of 150 kilograms. The horse has a mass of 440 kilograms. The horse pulls the cart with 75 newtons of force. So the force on the cart by the horse is equal to 75 newtons, okay? You should automatically know Newton's third law pair, force on the horse by the cart is equal to, all right, you need to write that down because it's the only place you're gonna find this information. So here are the problems. 1A, draw and label a free body diagram for the horse. It should be quantitative. What that means is that you can find numbers for everything. So it should be quantitative. So the length of each force arrow is proportional to the size of the force. All right, that's the first one. 1B, draw and label a free body diagram for the cart. Should be quantitative, include numbers that are known or that you calculate. Okay, number 2, what is a possible numeric value for how hard the cart pulls back on the horse? Okay, so what this is looking for is what is the force on the horse by the cart? Justify your answer. What is a possible numerical value for the forward force on the horse? Okay, so forward force on the horse. There's actually a range of values. There's a minimum value, and then, or it could be maximum value, but minimum value, and then, so there are lots of numbers this could possibly be. You just have to give one and justify your answer. And then what is a possible numerical value for the friction force on the cart? Again, this one, there are multiple possible answers. You just have to give one of the answers and say why it is correct.